Okay, welcome back, everyone. Today's speaker is Marion Villenave. She's a postdoctoral fellow at JPL, and if I got it right, received a PhD in 2020 from IPAC, France. Yeah. And then she works on the protoplanetary disks and planet formation, especially dust evolution mechanism in the disk, particularly in vertical settling and radial drift, and multi-wavelength observations, especially high resolution observations. And you also are interested in radiative transfer modeling. So that's today, Marion is going to talk about probing protoplanetary disk evolution using multi-wavelength observations. So Marion, the floor is yours.
Thank you. Hello, everyone. Thank you for being here. So yes, today I'd like to discuss, present some work on probing protoplanetary disk evolution, and in particular, I will be focusing on probing vertical settling within disks. As you know, protoplanetary disks are a stage of star formation. Star formation starts from the collapse of a molecular cloud, which will form a protostar surrounded by an envelope, and then the envelope will collide to form a disk. In that disk, the dust density is increased, and so it's easier for those particles to collide and stick and then grow to bigger sizes and form the planets. After some time, the disk has dissipated, and so we are left with stars surrounded by planets. And so, as I said, planet formation needs to be efficient because it needs to occur before disk has dissipated in a few million years. The standard scenario we assume for planet formation is the core accretion scenario that I described, where small particles can collide and then stick and then grow to bigger sizes. This scenario, however, is a bit slow unless there is a high dust density in some region. In particular, if we have a region with a gas-to-dust ratio close to 1, then the streaming instability can develop and it can form a climaticized body in hundreds of years based on from smaller particles. Also, if the dust density is higher, then there will be more collision between the smaller particles, and so they can grow more easily. And so in that context, it's important to understand the morphology of protoplanetary disks to understand where are the high density regions and what impact does it have on diversity on planet formation. And in this talk and in my work, I'm mostly interested in one mechanism which allows to increase the dust density, which is vertical settling. So vertical settling is a balance between the stellar gravity and the turbulent mixing. The stellar gravity will tend to make the grains fall into the midplane vertically, well, also radially, and also, and on the other hand, the dust and gas coupling, the turbulent mixing, will prevent the grain to go completely towards the midplane. It allows to mix again the grains so they can be a bit higher in the disk. This depends on the coupling of dust and gas, and so this is a size-selective mechanism because smaller grains like the smoke that I draw here will be very easily coupled to the gas. So it will be always well mixed with the gas and located where the gas is, while on the other hand, bigger particles will be like these little rocks that will be more hard for the gas to move around, and they tend to be more affected by vertical settling. And so because of this size selective efficiency, we can use multi-wavelength observations which probe emission from different grain sizes to study vertical settling. And because it is a balance between the stellar gravity and the turbulent mixing, obtaining constraint of vertical settling allows to understand better this turbulence, which are so two ways and goals of studying this vertical settling. So as I said, the impact of planet formation of vertical settling is positive because it allows to accumulate the dust in the midplane, and so it allows to increase the dust density in the midplane, which is favorable for planet formation. The other mechanism that I haven't talked too much about, but is also a balance between stellar gravity and turbulent mixing, would be radial drift. But this mechanism has a negative impact on planet formation because it will remove dust from the outer disk. And so if constraints on these two mechanisms is important because it can allow to better understand how these planets are forming. And so, as I said, we can use multi-wavelength observations to study vertical settling. And in particular, I compared two types of observations. So one type would be millimeter observations, such as with ALMA, that probe the thermal emission from millimeter-sized particles that would be more affected by radial drift and vertical settling. So here I showed two examples of this. So I am loopy, which is not so inclined and has clear rings, and TOE for 2021, which is more inclined, and so we are seeing this elongated rectangular shape. And now I'm going to show the same disks probe with scattered light image with sphere and HST. And as you can see, they look very different. And this is because we are not probing millimeter-sized particles, but we are now probing micron-sized particles, which are well coupled to the gas. And so as you can see, for example, I am loopy. In the scattered light image, we start to see the ball-shaped structure of the disk, while in the millimeter, the disk looks completely flat. This is showing that the gas is more extended vertically than the millimeter-sized particles. And so this is indicating that settling is actually happening in this disk. Similarly, in TOE for 2021, on the right, you can see that the millimeter grains are concentrated into a very thin rectangular shaped region in the center of this scattered light, more elongated, more extended at least shape. And so these two observations between scattered light and millimeter, they're very complementary, and they can allow to probe this mechanism of vertical settling and radial drift. And as I said, today I'd be mostly interested in trying to, in presenting observation of constraints on the vertical structure of protoplanetary disk, because it is not well known yet, not well constrained observationally, and so these are new constraints. And also, if settling is efficient, then this allows to increase the dust density in the midplane, which is useful for planet formation. And so there were evidence for vertical settling already some time ago based on a spectral energy distribution. As you can see in this plot, there is a clear difference at 100 micron between, so these are models, a model without settling and a model with settling. If there is no settling, then the flux at 100 micron is much higher than the flux when there is no settling at these wavelengths. And so these predictions were actually observed and confirmed in a very large number of systems based on spectral energy distribution. However, this is showing that there is vertical settling, but spectral energy distribution are very degenerate with many parameters. So it's not possible just from the spectral energy distribution to evaluate what is actually the level of vertical settling. So to do so, we need direct observations. And one type of objects that are particularly interesting to study the vertical extent are highly inclined disks, hadron disks. And so I'll first spend a bit of time to show what are some characteristics of hadron disks, how can we find them, which one do we know, and then I'll present some results that we find that exist on the vertical extent of the gas and small grains, and then I'll go to what are the new constraints we can get from the millimeter-sized particles expected to be more affected by settling again. So hadron disks, they will be seen very close to 90 degrees of inclination, and in that case, it has a big effect on the spectral energy distribution. So here I'm showing some models with just changing the inclination between 75 on the left and 90 on the right. And as you can see, when you increase the inclination, you start to see this double-shaped structure, peak structure, which is typical of hadron disks. So what is possible to do is to compile SED from the archive and then select which ones are likely to be hadron disks. And then you can use HST observations to confirm them as hadron disks. And as you can see here, if the disk is not very inclined, then you start to see the star emission directly, and so you don't resolve the disk. However, if the disk is sufficiently inclined, then the starlight is directly blocked by the disk. And without a coronagraph, we can directly resolve and see very well the disk with these two nebula structure. So what we see here is we see the two sides of the disk separated by a dark lane, which is due to the fact that the dust is very optically thick and it doesn't allow the starlight to escape from the midplane here. Okay, so this is how we can select this edge-on system. And again, these are interesting because we can directly see the vertical extent of the disk. So we can directly study their vertical structure. And so the method I described, this is what Carl and colleagues have done in the past, Carl Stapelfeld, and they have gathered about 30 edge-on disks that have been compiled so far, which is a bit less than what we could expect from the full population. And actually, the new analysis that Isabel Angelos performed and has almost submitted show that this selection is biased towards very inclined, also massive and extended disks. But this is observation of edge-on disks are interesting because they can allow, as I said, to directly constrain the vertical extent of what we're seeing here, which is micron-sized particles well mixed with the gas. And so here I'm showing a subsample of 12 disks that we also have other observations that I'm going to show later, where there were some models of the scattered light image for all these red boxed systems. And for all of them, the typical gas scale height is between 7 and 15 AU at a radius of 100 AU. So for this system, we know very well what is the gas scale height, and so it would be direct to compare with what is the scale height to determine what is the efficiency of vertical settling. But edge-on disks are not the only disk for which we can estimate the vertical extent of the small grays and the gas. Lower inclination system with rings can also be used. So here I'm showing an example of one way of estimating what is the vertical extent of a disk from scattered light observation based on a paper from Henning House. In this paper, he used the fact that if the height of the emission of the scattered light, for example, is high, is not zero, then the rings will appear off-centered of the different heights. And so based on this, we can estimate what is the height of the emission and reconstruct here the scattered light surfaces. In this work, they found that the typical scattered light surface for this disk is 16 AU, which is a bit more than what was found in other in previous works that I mentioned. But this is consistent because the scattered light surface is not directly the scale height. This is the combination of scale height and also optical depth effects. So the scattered light surface can be a bit higher than the actual dust scale height. Dust or gas scale height. So this is showing scattered light surface, but which is an indirect tracer for the gas scale height. But we can also now directly estimate what is the height of the gas emission surface based on the channel map seen in a millimeter. So here I'm showing again IM loopy, which is a disk that has been very well studied. One channel map of emission over 12 CO, where we can see that we resolve the front side of the disk, which is brighter, and also the back side of the disk of the emission, separated by a dark region, which is the midpoint. And so based on the fact that we can resolve both the front and the back side, it is possible to use geometrical analysis to estimate what is the actual height of the system with radius. And so this has been done in a number of systems now, and the typical height for the emission surface gives a Z/R ratio of 0.3, which is slightly dependent on the stellar mass. So as you can see here, these are estimates from the recent law paper from 2022, where he finds that the height of the emission from the CO slightly decreases with the stellar mass, which would be consistent with what we expect for the scale height, but is not direct because, again, we are probing the emission surface rather than the actual surface density, gas scale heights. Now I showed you some estimates of the gas emission surface and of the scattered light emission surface, and we can also compare them together. So here I show on the black, this shows the gas emission surface, while the green points or pink points correspond to the scattered light emission surface. So what this works found is typically that at smaller separation from the star, less than 100 AU, the gas and the scattered light emission surface are coincident, while if you go to further radii, then the scattered light surface is lower than the CO surface, which is likely due to optical depth effect. The CO would be more optically thick than the scattered light, or more quickly optically thick than a scattered light, and will appear higher than the smaller grains. Okay, so here I presented some results on what is the typical vertical extent of the small grains in the gas, so which is between 7 and 15 AU at 200 AU. And what we can see from direct observation has to be modeled so that we reconstruct what is the actual gas scale height. But what I'm very interested in is to know what is the vertical extent of the millimeter-sized particles, because the millimeter-sized particles are those that are expected to be more affected by settling, and those that are going to grow by sticking and to grow to form these bigger particles, pebble planets. And so I'm going to go quickly into what can we do with low inclination systems. Basically, I think I would say that this is hard to do, to measure the scale height of millimeter-sized particles for low inclination systems, because we need a precise modeling of the rings and gaps. In particular, we can use, for example, projection effect. If we use models with a scale height that is too high, then it will fill in the gap of, for example, h and tau, and we can determine what is the limit for what is the vertical extent. However, we need to have a series of rings and gaps very close to each other to perform this technique, and this is not so common in disks in general. There is another technique that was used by Doi and Kataoka on HD 163296, which was to use the variation of intensity between the different parts of one ring, finding that if it doesn't vary, then it means that there is little settling, while if no, and the opposite, if it's does not vary, it means that the disk is very thin, while if it does, then it means the disk is not so thin. And so the results on these two systems typically find that the scale height of the dust is 1 AU at a radius of 100 AU. And in HD 163296, they also find that the scale height of the dust is probably higher for the inner disk, like 67 AU. These constraints on dust particles are interesting, but they are they're limited to the millimeter dust. What would be interesting to get is to have at the same time the millimeter dust scale height and the gas scale height. And as I presented before, the edge on disk, there is a number of edge on disk for which we already have a good constraint on what is the gas scale height. And so I'm going now to focus the rest of this presentation to show some new results that we obtained from this edge on disk, and in particular from new ALMA observations, well, new from 2020. So here I'm showing again the scattered light observation from micron-sized particles in the colors, and millimeter-sized observation showing millimeter dust, which is represented by the contours here. So what you can see in all these systems is that the contours look much less extended both in the radial and in the vertical direction compared to the colors. So the millimeter dust is less extended vertically and radially than the micron-sized particles. And this is consistent with vertical settling and radial drift. But to really quantify how efficient these mechanisms are, we need to do radiative transfer modeling. And so in this work from 2020, what we did is we chose the 3 most interesting systems, and we performed fiducial radiative transfer modeling to estimate what is their vertical extent. And so these are the 3 disks that were more interesting to study, which are HA30, HK2B, and HH48. They are more interesting because they show very typical radial profile with very sharp edges and flat top, which is indicating that they are optically thick. In the minor axis direction, they were not always very well resolved, but they look like a Gaussian with a vertical extent of 0.1 or 0.2 arcsecond. And so what we did is that we performed 4 radiative transfer models, or with a high mass, a low mass, and then with settling or without settling for different inclination. And we wanted to see if we can disentangle between the with settling and without settling in this system. And so now I'm going to show you the prediction for the radiative transfer model for the radial profile. They are shown here. On the left, you have the high mass model. On the right, you have the low mass model. And then the colors, when you go from darker to clearer, is increase of inclination. So as you can see, when the inclination is low, 75 degrees of inclination, we have a very centrally peaked profile. While if we increase the inclination, then the disk gets more optically thick, and we get to have a less and less sharp profile and arrive to a flat top, in this case, at 90 degrees for the high mass model. For the low mass model, it never gets sufficiently optically thick to arrive to the plateau. So this is why we concluded that our disk must be closer to the high mass model. And so from this, we compared what do the high mass model look with and without settling, which is shown here. You can see that there is a very clear difference between with and without settling. With settling, the disk looks very flat and rectangular, like our systems, while if there is no settling, it looks much thicker, and there is also a lower intensity lane here, similar to what is in the HST images, but in the millimeter. So this is showing that our systems were mostly compatible with this high mass model with settling. And so they were compatible with having a scale height of about 1 AU at 100 AU, which is consistent with the results also from Postdoctoral and Dio and Ketoka. So now if we go back to this plot, you can see that for HS30 and HK2B, we have some constraints both on the gas scale height and on the millimeter scale height. For the rest of the system, we would need detailed modeling to obtain constraints on what is the millimeter scale height, the scale height of these big grains. And today I'd like to present some results from this recent paper on 1631-31, this green box, and some work in preparation on this RS-04302. So why is this of 1631-31 interesting? Well, first, it has been modeled previously by Skylar Wolf, who is actually in Tucson. She did a model of both the scattered light and the ALMA images together, showing that to reproduce both together, we need some level of Earth gas settling. And also the model she performed was allowed to constrain very well what is the vertical extent of the small grains. It is about 10 AU at 100 AU, which is consistent with the previous results I was showing before. But this observation that was used in the paper, it was not resolved in the vertical direction, so we could not get very good constraints on what is the settling efficiency in the system, and better observations with higher angular resolution would be useful for this. This paper on the ALMA and HST model was also followed by another paper from Christian Flores, who focused on the gas observations, where he determined what is the stellar mass of the system, and also produced this temperature map of the 12CO, where we can see the disk plane, which is colder than the upper and lower surface of the disk. I also have a higher angular resolution map like this. If you're interested, I can show it at the end. Okay, and so as I said previously here, I'm interested in what is the vertical extent of these millimeter-sized particles. And so what we obtained was new observations on that system with a resolution that is, instead of 30 AU like here, it would be a resolution of 3 AU. I'm showing here the new image that we obtained, and it looks very different. If you look at the previous one, disk could be imagined to be edge-on. However, with the new observation, we clearly see a ring structure, which indicate that the disk cannot be 90 degrees of inclination. Instead, it is more closer to 84 degrees of inclination. Here, I did some layouts where you can see that there is very clear structure. We have an outer ring, a clear gap, and then inner ring and central region that is very bright. And the presence of this outer gap, the gap 1, is very interesting because it means that seeing it means that the disk must be very thin, because if it wasn't so thin because of this projection effect, then we would blur out the gap and we would not be able to see it. And so we wanted to use these observations to constrain again what is the vertical extent of that system. And to do so, we first started with a simplified parameterization of vertical settling, where we used the constraint from scalar on the gas scale height to be, which was 10 AU at 200 AU, and then we tried different values for the big grain scale height, between 0.5, 1, 2, and 3 AU at a radius 100 AU. We modeled the system with MPFOST, and then we produced synthetic images with the CASA simulator. And this is what we're going to look at. So on the left, you have an image of the data with the two cuts we performed. On the right, top right, you have what the cut along the major axis look like at the zoomed in at the position of the gap. And at the bottom, you have what the cut along the minor axis look like at the position where we did it, and where we see that it has 3 peaks. The 2 outer peaks correspond to the outer ring, while the inner peak would correspond to the inner ring. And the fact that we can see the 3 peaks is what is the constraints we're going to use to determine what is the height of the emission for the disk. So as I said, we perform 4 radiative transfer models with different scale height of 0.5, 1, 2, and 3 AU. You can see that as we increase the scale height, the gap at the position of the cross is less and less clear, which is what I was calling projection effect before. Now on the right, I showed what do the cuts of the model with scale height of 2 AU and of 3 AU look like. You can see that the major axis cut isn't as deep as what the data look like, probably already due to projection effect. But more clearly, on the minor axis cut, we now have just 1 peak instead of 3 peaks. So the gap is so thick that we are not able to resolve the gap in this minor axis direction. So these models with a scale height of 2 AU and 3 AU can be excluded. They are really too thick to reproduce the data. Now I'm going to add what the cuts for the model with 0.5 and 1 AU look like. So you can already see that in the major axis cut, they are deeper, and so they're better. But also on the minor axis cut, we now have the 3 peaks. The red curve, which is the model with 0.5 AU, is the one which matches best the data. And so this is showing that our system, this disk has a scale height of 0.5 AU at 100 AU. This is a bit less than what has been constrained in the other systems. And this is significantly less than what the gas scale height is, which is 10 AU. So here I showed again, the gas is not 10 AU, and then dust is 0.5 AU. And we can use this constraint to determine the implication for a degree of dust and gas coupling. Indeed, in the classical prediction for 1D prescription for settling, we have a direct relationship between the dust scale height and the gas scale height as a function of the Stokes over alpha parameter, alpha over Stokes parameter, where alpha would be the turbulence and Stokes is the coupling of dust and gas. If we take the numbers we have, we find this constraint on the Stokes over alpha over Stokes ratio, less than 10 to minus 3, which is small. And also what we can note is that this equation here is also valid in the radial direction, but in the radial direction, the ratio of gas to dust is significantly less than in the vertical direction. This would imply a much higher value of alpha over Stokes. So this would imply that the radial turbulence is stronger than the vertical turbulence if this approximation, this classical 1D prescription is valid. And this is consistent with what has been found in HG 163296, where some estimates on the radial alpha over Stokes find a bigger value than the estimate on the vertical. So these observations would suggest that the turbulence level is different between the radial and the vertical direction, vertical turbulence being less strong than the radial turbulence. And this is interesting if it was performed in more systems, because we could compare with prediction from models. And this is one prediction from the vertical shear instability, where you can see the deviation or the perturbation in the radial, in the radial direction, in the vertical direction. Without looking at the numbers, we can see that in the radial direction, the perturbations are much less important than in the vertical direction. So this is contradictory to what we find in these two observations, which are still a bit tentative. And so further observational results, observational constraints on this radial and vertical turbulence are important, and also numerical prediction could be useful to help to understand better the origin of turbulence in disks. What we can also do for this system is to determine the turbulence level directly without its coupling with the Stokes number by using a parametric prescription for vertical settling. So we used, in this case, the prescription from Poma and Nelson, for which the vertical density depends on the grain size, gauge scale height, surface density, and turbulence parameter. And so here I'm showing two models, several models. On the left, you have the data, and then you have a model with the turbulence parameter alpha of 10 to minus 5, 10 to minus 4, and 10 to minus 3. Again, as we go from left to right, we can see that the outer gap is seen less and less clearly. The best model being the model, the first left model, which is alpha 10 to minus 5. So this is a very low value, which is much lower than the value estimated by Christophe Pant on HL tau, or by Kevin Flaherty on other systems using the gas. Altogether, this suggests that turbulence is low in the outer regions of protoplanetary disk, which also is interesting and has implications for planet formation. So the last thing that I would like to present for this system is that the constraints that we obtained for the vertical direction are very useful to understand planet formation. And the reason why is that we try to estimate the timescale necessary for pebble accretion. So let me go through the plot slowly. So the observational constraint that we obtained were the dust to gas scale height ratio. We find that the gas scale height is 20 times higher than the dust scale height, and this would correspond to this blue line in the plot. And then what we wanted to see is how fast can a lunar embryo grow to a 10 Earth mass planet at 100 AU from the central star. And these contours here show how long it would take to grow from a moon to 10 Earth mass. And then we had to assume the gas to dust ratio. If we assume a gas to dust ratio of 100, we get this red line here. And in that case, it would mean that 10 Earth mass planet can grow in 3 million years at 100 AU. In our worst case scenario, which is the orange line here, we still are able to form a 10 Earth mass planet in less than 10 million years, so in the typical disk lifetime. So this result is really linked to the fact that the pebble scale height is significantly lower than the gas scale height. If it was higher, then we would probably not be able to form planets so fast. As you can see, the blue line would go to the right. And so this is the conclusion written here. The pebble scale height strongly promote cloud growth. And this has actually implication, and it means that maybe it is possible to form wide orbit planets in the disk if they are very settled. So if we go back now to this survey of edge on disks, so we have now described the constraint that we obtained on 3 disks. HK2B, HH30, HH48, for which we compare them with a fiducial radiative transfer model, find a scale height of 1 AU is okay, it's a good match. Detailed modeling above 1631 here shows that less than 0.5 is our constraint, and it means the turbulence will be less than alpha 10 to minus 5. And so now I'd like just to show some quick preliminary results on this new system here, RS04302, which is interesting because it's a younger system. So you can see, well, I go back here. You can see that the scatter light image here in the color looks much more complicated than the scatter light in the HH30 or 204 2021. It is not uniform, homogeneous. Let's say it has all these blobs. It was actually called the butterfly star, this system. And the fact that we are seeing all these structures mean that this is a younger system and we are looking at an envelope. And so this is a class 1, while before I was showing results on class 2 or 1-2 systems. And for this system, we have new VLA observations that are shown here. So first, what we can see in this system is that, again, the ALMA observation is much less extended vertically and radially. than the HST image, but this cannot be compared as easily as before because now we are seeing an envelope in the scattered light. So it is not a direct evidence for vertical settling and radial drift. But then we can also see that the VLA observation, so at 1 order of magnitude bigger wavelengths and grains, it is also much more compact than the ALMA image. And so this is maybe suggesting that the big grains are more concentrated inwards, or maybe this is just optical depth effect. Also, interestingly, in these observations is that the ALMA 2.1 millimeter here is well resolved in the minor axis direction. So we can probably use it to constrain what is the vertical extent of the dust. And so here I'm showing very preliminary results. They're maybe going to change, but I would like just you to focus on this in the center, which is a minor axis cut of this well-resolved bond 4 data. You have the data here in blue. And what I would like you to look at simply is to look at this yellow line here. You can see that it is a model with a scale height of 1 AU, and you can see that it clearly does not match the bond 4 actual vertical extent. And so this is suggesting that the model with 1 AU of scale height is too vertically thin to reproduce the vertical extent of the observations. And so this would be the first lower limit on the scale height at millimeter wavelengths. Of course, we have more parameters to test, so this is not final results, but this is interesting, and it could mean that we are seeing some time scale for vertical settling. And here I made this very simplified plot, but summarizing the results. So here on the left, you have two class 0 systems for which the authors mentioned that there is no settling at all. Our new results on IRAS 04302 suggest that the disk is at least more extended than 1 AU at 100 AU. And then many results in class 2 disks tend to say that the disk must be less than 1 AU at 100 AU. So probably this class 1 system is intermediate between the class 0 and class 2, and so it can allow to help to understand the timescale for vertical settling. And more observation of this kind of disk would be interesting in testing this idea. And finally, before concluding, I would like to mention that we have cycle 1 program JWST observations for edge-on disks. The idea is to observe these 4 disks at 5 different wavelengths between 2 and 20 millimeters, and to try to determine the level of settling at this intermediate wavelength, so intermediate grain sizes. And the program should be executed between January and March in the coming year. And so, yeah, I'd like to just conclude. I presented some results, mostly on edge-on disk, which allow to directly see the vertical extent of protoplanetary disk and to compare directly some previous results on scattered light and new results on millimeter observations. And I focused a bit more on this new results on the high angular resolution observation of OBCC 3131, where we find that the millimeter dust is more than 10 times smaller than the gas scale height in height. Sorry. Now the turbulence must be low, and the implication for planet formation are direct, because we show that thanks to this very low dust to gas scale height, we can probably grow a core of a lunar embryo to a 10 Earth mass in less than the disk lifetime, even at 100 AU, which is very far. And so, yeah, future work for this would be to work at this JWST data and also continue on to obtain constraints on class 1 systems. Thank you for your attention. I'm happy to get questions.
Okay, that's Marion, wonderful talk. Okay, question. Let's see, Caitlin.
Hi, sorry. Yeah, thank you for that very nice talk. I just have a question that maybe is beyond the scope of a simple answer, but I'm just wondering about the observational distinction between differential grain growth and vertical settling. Like, is that something that you think could ever be constrained?
This is hard to say. No, it's a very good question. I don't think that right now we would be able to say the difference for 2 reasons. One reason is because we don't have clear predictions on how different those two would look like, because there is no model that do vertical settling and grain growth at the same time. So I think this would be one first limitation. And the other limitation is that there is only one system for which we could resolve the vertical extent at 2 wavelengths. And so this is also a bit limiting.
Yeah, I know it's phenomenal result, but okay, thank you.
But this would be very interesting to do. Thank you.
Okay, Andrew.
Yeah, hi. Yeah, thanks again for the talk. So yeah, obviously the difference in radial and vertical turbulence is something that would be very nice to understand. And this is a great step in that direction. I wonder if you could discuss a bit sort of how robust do you think the observational constraint is? So the vertical part obviously comes from settling, and I think you said that the radial part comes from disk sizes. And I guess both of those are model dependent in different ways. So based on that, I mean, how strongly would you bet that these are in fact significantly asymmetric?
Right now, I don't really know. I don't think it is extremely strong. Also because for the so yes, the vertical direction, this is due to this is made with a model of vertical settling. This I think is quite robust because I mean, of course, it's model dependent, but it's also geometrical effect that we're looking at. So it is quite strong. It's not only model, but then on the radial direction, what is done now is what Kees Delemont has done on his T-sharp paper, and so basically he had to assume what is the gas scale height in the radial direction, and then this has implication for what would be this. And so he assumed the gas scale height, he measured the dust width, and then from this we can get what is the alpha over Stokes ratio. So this is still more model dependent, I would say, than the vertical constraints. But what they found using this is a lower limit for the radial direction and an upper limit for the vertical direction. So it seems still to be in contradiction, I mean, not in agreement, even if it's very model dependent, I don't know. But okay, of course, it's 1-2 systems. So it's I mean, there is more to do to complete the story, to be sure of it.
Sure. So just so I understand, the radial constraint is from the width of dust rings. Again, assuming that that was the Kees Delemont result you're referring to.
Yes. So they use the same formula as I put here, but for the radial direction, and then they had to assume what is the width of the gap in the gas of the ring in the gas, and measure the width of the ring in the dust, and from this they get a value for alpha over Stokes.
It'd be nice to measure those gas rings.
Exactly. It would be very good, yeah.
Okay, thanks a lot. Yeah.
Thank you.
Okay, there are 2 questions in chat. So first one is from Xiaohu. Would you like to speak up, or shall I read it?
Oh, sure, I can. Yeah, I can talk about it. So, I ask this question because I guess for those dust modeling for the synthetic images, you usually assume the midplane is perfectly flat. And in some of my MHD simulations, if we use a weak magnetic field, so there's not much turbulence in the simulation. We see a very sufficient settling, as you predicted, but we still see the midplane is not a plane anymore. It's been distorted by, say, about half scale height. So I was wondering if this effect, I mean, while the dust layer is still very thin, how would that change the synthetic image or observation?
So do you mean the prediction in the millimeter or in scattered light? I wasn't.
I think I mean in a millimeter. Yeah.
Yeah, I guess it depends on how strong the effect is. But
yeah, about half the gas scale height.
Half the gas scale height. Yeah, then I guess we should see one thing on this agent survey is that the resolution was 0.1 arc second, so not all the disks were resolved. So this is one difficulty. But yeah, for OP 163131, I guess that this one, the one that has the rings, I think we should be able to see if there is a half a scale height variation between within the disk. But I guess I should see what the prediction look like to be able to give a better answer. Because I think this is interesting. Maybe we could see it if we had a better resolution and if we're actually 90 degrees.
Okay.
Also. I'm not so sure. Thank you.
Okay, now Richard Gordon, Richard, would you like to ask a question directly? So Richard's asking, might tomography be possible with enough similar disks? I think you showed one paper, kind of, but how many do you think you can do tomography?
Yeah, I can show this.
Yeah.
This is the newer angular resolution data. So I think this kind of map can be done for all of the systems that we have, all the 12 agencies for which we have observations. So, however, here we have, here we clearly see the two sides of this because we have a very good angular resolution. When we have less good angular resolution, then we can get a temperature map. However, it will not be as precise as this. And also, when you have a bigger beam, then you integrate the disk on a bigger scale. And so the peak in here would be lower. So I guess the information on the midplane temperature and other parts of the disk would be less constraining. But this can be done on more systems. We just need to know the inclination and the distance of the disk to produce this kind of maps. And we plan to do this actually, but this is ongoing.
Okay, I hope that answered your question, Richard. And Jess Speedy just asked to show, can you send a link to the paper in which you found that result? So that was a question to show. And any other question?
Yeah, I have a question.
Oh, sorry, I can see over your behind.
I'm wondering, is there any effect that brought by the jet on the scale height? Because we know there are jets in the protoplanetary disk. I'm not sure how far it can go by impacting the scale height of the dust or gas.
Yeah. So there are some of the agencies that we have that have jets. For example, you see HE30. I'm not sure how far this would impact, but I think that this is, if there is a jet, this would mean that the turbulence should be higher in the disk, and so we should see a disk that is more vertically extended. For example, in OP 163131 here, there is no jet, and the turbulence is alpha 10 to the minus 5, and the vertical extent is very low. So I don't know how closely this is related, but yeah, certainly the presence of a jet should have likely has an effect on what is the vertical extent. Maybe Carl wants to can say more. I see your hand.
Oh yeah, I was just going to add a comment, Marion, which is that I don't think that the flow of the jet so much would produce an effect. That would be strongest, the inner disk, which we aren't generally sampling too well. But instead, if the stronger jet means a higher accretion rate, which then probably means a warmer disk throughout, and therefore you get a higher scale height from that as a maybe not causation but correlation.
Okay, talking about accretion, I was going to ask about do you know well about the accretion rates for these systems? And did you?
I don't think we know it for all the systems.
I was wondering if there was any correlation with accretion disk and then what you're finding as well.
Yeah, I think it would be interesting. I don't think we have. We didn't do it yet. We just know in the images if they have jet or not. And we could do the correlation job, but this is not, we have not done it yet. I think that, well, actually I had looked at it quickly for the gas extent, and it's not clear if there is a correlation, but this should be done more precisely to check.
Any other question? No,
I'm good.
oh, you're good. So I had one more tiny little question. There was a plot showing that I think scale height versus stellar mass correlation.
Yeah.
Yeah, I think there was only, I was wondering if there was actually a strong correlation, because it seems like there was only one low mass, is that number 10 and 18? There are two sources on, is it, are there two sources at the 0.5 service?
Well, these are not too far from 0.5.
Yeah, but the upper ones. So I was wondering how strong that relation was. I just wanted to confirm that.
How, so, sorry, can you?
Yeah, the sources, the 10 and 18.
I don't know now, but it is in the low ETA 2020.
Okay, yeah, I'll go and look for it. Thank you.
Thank you.
And who, is there any other question?
This is Carl. I was just going to comment on that again.
Okay.
You know, we have trouble getting the masses of these unless there's ALMA data at sufficient resolution to get a dynamical mass. So there's that. I mean, there is one example of a fairly low mass central star where we do see a relatively high scale height, and that's in Skylar Wolf's 2017 paper doing the scattered light modeling for ESO H alpha 569 as a larger scale height in that low mass edge on disk system than in the other ones that Marion was reporting. But this is only for the scattered light. We don't have that data for the millimeter continuum.
Yeah. And this is from lower inclination system.
All right, thank you very much. Okay, last call for question. Yeah, otherwise, let's thank the speaker again, and we'll see you next week.
Thank you.